John Levesque here again. This video we'll be talking about perftools-lite-loops. Now, once again, extremely easy to use. All you have to do is make sure that you have perftools base and perftools-lite-loops loaded, the modules loaded. Then you make your application as usual, run it as usual, and then we'll analyze the results. Alright, notice that we now have perftools-lite-loops loaded instead of perftools-lite. And we also have perftools base loaded. Have to have those two loaded, and using the same application we've used in the first two videos. And we'll do a make. Now, one thing that's extremely important here, when we gather instrumentation on the loops, OpenMP directives are ignored because of course, if you have OpenMP in the program, it would be very difficult for the compiler to figure out the iteration count that each of the threads were using. So OpenMP directives are ignored. Notice we still have the -h list equal a, so that we can look at the code. And now we have a executable. Now this is not a sampling run. This is actually a trace. In order to gather those loop statistics, there are instrumentation inserted around every loop in the program. Alright, now we're going to submit the run. Notice that we do everything exactly the same as when we were using perftools-lite. So it's very easy to use these tools interchangeably here. Okay, so our execution has finished. We have our output file. Notice now we have a directory with a T for tracing rather than an S for sampling in the previous video. So what we should see is the loop information at the end of this output. So let's see. Here is the output from the application itself. Now this runs a little bit longer because when you instrument the loops, it is going to take a little longer to run. You don't get all of the information from perftools-lite in these preliminary tables, but what we're actually looking for is this here. Very useful information. What it's saying is that this loop is actually uses 99% of the time. It is encountered once in the whole program. It actually has 50 average, min, and max. Alright. Now, this runs 100 cycles. It turns out that each iteration of this loop runs 2 cycles. And so that's why this is 50. So this sweep Y is actually encountered 100 times, twice for every one of these. And the average, min, and max are all 32. Now, from the line numbers, it looks like this loop is nested inside this loop. And it is encountered 3,200 times, 64, 64, 64. You see there's some other loops down further that are all 64. Then we have the loops in sweep Z. Notice that these are ordered in those loops that use most of the time. All right, and now, unfortunately, this is not the right way to look at this display. The best way to look at this data is in the call chain. So what we're going to do is do a pat report, and we're going to use call tree, and we're going to give it this, and we're going to output it to profile. Loops call tree. And now we will look at this. Now, this really shows us what's going on. All right. What you see in front of you is an indication that this particular loop should probably be investigated for threading. It is a high-level loop. It uses a significant amount of time. Now, it turns out that MPI uses a lot of time, as we saw in the previous runs. But of the user time, this really uses a good amount of time. And notice the call tree underneath it, PPMLR. So what we have here is a double nested loop. And then we also have loops down in here that are not indicated because they use less than 1%. This is a good place to introduce another option here. So I am going to do the same thing, and I'm going to use a T. Basically what that says is to profile or display everything, even those things that use less than a percent. All right. So now, notice that we are getting everything. So this is a fairly deep call tree that, in fact, is parallelizable. So we have the one on sweep Z, and then it turns out we have another one on sweep Y, and a third one on sweep X2, and a fourth one on sweep X1. So all in all of the computation can be threaded. And the loop lengths, this is one thing I've asked for. I'd love to see the loop lengths on this particular display. But what we do know is that one of these loops is 32 and one is 64. Well, the other two. There are 3 dimensions. One is 32 and the other 2 are 64. So that gives us a very good idea of where we should look for inserting OpenMP into this application. We wouldn't want to parallelize the loops in those low-level routines. We really want to parallelize the high-level ones, if possible. In a subsequent video, I will actually go through an analysis of this loop for shared memory parallelization to show you what you need to look for. So, that was a pretty short video. The next video will now use this report to look at the application.